In this tutorial, we are going to study the second sequential circuit, that is a JK flip-flop. In the previous lecture, we have studied about RS flip-flop and its working. In today's lecture, we are going to study about a JK flip-flop. This is the logic diagram for a JK flip-flop, which consists of 4 NAND gates. Let me number them. This is NAND gate number 1, 2, 3 and 4. You can observe that the logic diagram for JK flip-flop is similar to SR flip-flop. Only one modification is done over there. That here instead of 2 input NAND gates, we have used 3 input NAND gates, NAND gate number 1 and 2, and there is one more connection from the feedback path. So this Q is connected as an input to second NAND gate and Q bar is connected as an input to first NAND gate. So this is the logic diagram for JK flip-flop. Now we have to check the output for these JK flip-flop for the different set of inputs. Look at this truth table. In truth table, the first condition is that if the clock is 0. If the clock is 0, then what is going to be the output? So let us assume that this clock is 0. And there is a don't care condition for J and K, means whatever may be the status of J and K, what is going to be the output that we have to write. So here if the clock is 0, then output of first and second NAND gate will be forced to be equal to 1 irrespective of the other inputs, that is J and K and Q bar. Because if one input of NAND gate is 0, its output will be obviously 1 irrespective of the other inputs. So if the clock is 0, then the output of first and second NAND gate will be 1. Now let us assume that the previous state is 0, 1. So this 0 goes here, 0 and 1 is 1. Then this 1 goes here and this 1 and 1 is 0. So you can see that if the previous state is 0, 1, then it will remain in the same state, that is 0, 1. Now if you consider that the previous state is 1, 0, then in that case this 0 goes here, ये 0 यहाँ पर आ जाएगा, then this 1, 0 will be 1, this 1 goes here and then 1 and 1 will be 0. Now for this as well we have got the same output, that is 1, 0. It means that if the clock is 0, then whatever may be the value of J and K, the output will remain in the same state. As it is in the same state, it will be Q only. It is called as the previous state. Here we have to write it is previous state. It is in the previous state. Now let me erase these things and let us check the output for second input combination. Next input is clock is 1, J is 0 and K is 0. Clock is 1, J is 0 and K is also 0. Now in this case also, the output of first and second NAND gate will be forced to be equal to 1 because one input of each NAND gate is 0. This J is 0 and K is 0. Both the NAND gates will produce the output 1. Then if you assume that the previous state is 0, 1, then this 0 will go here, this will generate 1, then this 1 goes here, this will generate 0. Means output will remain in the same state. If it is 0, 1, it will remain in the 0, 1 state. If it is 1, 0, then also it will remain in the same state. So for this we have to write that it is again Q, or we can say there is no change or there is a previous state. Let it see. then we have to check for the next input combination. Next input combination is that clock is 1, J is 0 and K is 1. Now you can see that one input of first NAND gate is 0, so output will be 1. Now what about second NAND gate? For this, two inputs are already 1. We have to check for the third input, and for that we have to assume some previous state. So suppose the previous state Q is 0 and Q bar is 1. Right? Then this 0 goes here because this is given to the second NAND gate. 0 goes here. And the output of this second NAND gate will be 1. Then look at this. This 0 goes here. 0 and 1 will be 1. Here also this 1 goes here. 1 and 1 will be 0. It means that for 0 1 output, means if the previous state is 0 1 and if J is 0 and K is 1, the next state output is 0 1. So here we have assumed that the previous state Qn was 0 1, and then we have got Qn plus 1, that is 0 1. Okay? Now we have to check for another previous output condition. So let me erase this previous output and then let me check it. So assume that the previous state is 1 0. If the previous state is 1 0, then if the previous state is 1 0, then this 1 will go here, right? So this 1 1 1 will become 0, and then this 0 will go here. This will remain 1 only. And then look at here. This is 1. So output of fourth NAND gate will be 1. Then this 1 will go here, and 1 will become 0. So even if the previous state is 1 0, then we have got the next state, that is 0 1. Right? Means if the previous state is 1 0, then we have got the next output, that is 0 1. Means Q is 0 and Q bar is 1. Means in both the cases you are getting Q is equal to 0. That's why we have to write 0 over here. For J is equal to 0, K is equal to 1, the output will be 0. And this is called as reset condition. This is called as reset condition. Now we have to check for the next input condition, that clock is 1, J is 1 and K is 0. So let me erase all these things. Let us assume the next input condition, that clock is 1, then J is 1 and K is 0. Now here also we need to assume some previous state. Suppose Q is 0 and Q bar is 1. This is the previous state. Now this 0 will go here and this 1 will go here. So output of first NAND gate will be 0 and output of second NAND gate will be 1. Then this 1 goes here for the third NAND gate. So this 0 1 will become 1, and this 1 goes here and this 1 1 will become 0. So this is going to be the next state output, that is 1 0. And here we have assumed that the previous condition was 0 1 and we have got the next state, that is 1 0. Okay, we have checked for the first input condition, first previous output condition, that is 0 1. Now we have to check for one more previous output which is possible, that is Qn will be 1 and Q bar n will be 0. Let us check for that condition. Now if the previous state is suppose 1, 0, then this 1 goes here, this 0 goes here. So this will become 1 and this will be also 1. Now this 0 goes here, so 1 and 0 will be 1. This 1 goes here, 1 and 1 will be 0. If we assume that the previous state is 1, 0, then also we have got the output that is 1, 0, which is same as this. Means if the previous state is 0, 1 or 1, 0, in both the cases you get the output that is 1, 0. Means Q is 1 and Q bar is 0. So here we have to write 1. If J is 1, K is 0 and clock is 1, then your output is going to be 1, which is called as a set condition. Now check for the last condition. Last condition is that clock is 1, J is 1 and K is 1. Let us assume the previous state. Q is equal to 0 and Q bar is equal to 1. Q is equal to 0 and Q bar is equal to 1. The previous state is this. Now this 0 goes here and this 1 goes here. Output of first NAND gate will be 0 and output of second NAND gate will be 1. Then after that this 1 will go here from here because this is connected to third NAND gate. This is 1. 0 and 1 will become 1. Then this is 1. Now 1 and 1 will become 0. Now here you can check that if the previous condition is 0, 1, what the next output that is 1, 0. Means Q is 1 and Q bar is 0. Let me check for one more output condition. That is if the previous state is 1, 0, then we have to check that what is going to be the output. So if the previous condition is Q is 1 and Q bar is 0. In this case also this 0 goes here, this 1 goes here. Now the output of first NAND gate will be 1 and output of second NAND gate will be 0. Now this 1 comes here, the Q, and then output of fourth NAND gate will become 0. So it will become 1 and output of third NAND gate will be 1 NAND 1, that is 0. So if the previous condition is 1, 0, then you got the next output that is 0, 1. If Qn was 1, 0, then we have got Qn plus 1, that is 0, 1. In both the previous output conditions, you can see that your output gets toggled. Means if the previous state is 0, then you get the next state that is 1. If the previous state is 1, you get the next state that is 0. Means in both the cases, you get the output that we can say Q bar. It is the complement of the previous state. Here you can write this is Qn plus 1. So this is Qn bar. It is the complement of the previous state. And this mode is called as a toggle mode. And this is a very important state for the JK flip-flop because here the limitation of SR flip-flop is removed. In SR flip-flop, if we apply the input S is equal to R is equal to 1, 1, then we get the forbidden state or the not allowed state because both the outputs are forced to be equal to 1. But this drawback is removed in the JK flip-flop. In JK flip-flop is if J is equal to K is equal to 1, then your output will toggle. It will go in the toggling mode. Means if the previous output is 0, then you will get 1. If the previous output is 1, you will get 0. and this property of JK flip-flop is very useful while designing the counters using the JK flip-flop. So that's all for this tutorial.